So this section lecture, we're going to do a deep dive and look at some code. And so this is a very tiny implementation of dynamic symbolic execution for Python, written in Python. So you've already seen that Z3 has a Python interface. The Z3 theorem prover is written in C++, and Python has a very nice way of interfacing to C. So you've already seen me demonstrate the Python interface to Z3. Python itself is a dynamic scripting language. We're going to take a very small subset of Python and show how to implement dynamic symbolic execution for that. And so the source code's available on GitHub at this URL, Thomas J. Ball. Okay, I can't download. Guess maybe I'm not. Let's see. Discard. Oh, yeah, we're limited again. Let's see if we're. Oh, I need to log in again. Okay, that's fine. Okay, we're logged in now. Yeah, so let me just say a little bit about the source code. Yeah, so you can access it here at GitHub under the project pyxz3. There it is, and it has a little README. So you need to download Python, and you need to download Z3, obviously. And then there's some setup instructions there, and then I have a little regression test pass. So during this week, I hope you'll take advantage of the opportunity to try that out, play around with it, and if you want to work on that with me, I'm totally happy to do that. The code I did not write from scratch. I derived it from a project called the NICE project. This was a project for testing open flow controllers. It's a particular language, low-level language for programming software-defined networks. So they had a little symbolic execution engine that they wrote. I took that and ported it to use Z3 instead of the STP theorem prover. There were a number of platform dependencies in the code. I tried as much as possible to eliminate those, so it should run on Mac OS, it runs on Windows, but you may have some issues there we'll have to work through. The approach they used was heavily dependent on bytecode instrumentation, which is very Python specific and changes from version to version. So I changed that to use a instrumentation at the abstract syntax tree level, which should be a little more robust. And the other thing about the code was, although it was a nice little design, it was clearly created just for a paper and then never developed again. So it didn't have a lot of error validation on its inputs. It wasn't very friendly to get up and running. So I hopefully have done a decent job of improving it, so when you use it, you'll have a better experience than I did. The basic design points remain the same. It really only supports symbolic integers. So the only things you can talk about that it will symbolically reason with are integers. Python has lists and maps and dictionaries and all those things. So if you want to make a full symbolic execution engine for Python, there's a lot more work to do. But even with symbolic integers, you can see the sort of basic design. And Python has a particular way, well, like C++, it allows operator overloading, which is a particular nice way to do this concolic execution, where you have an expression that you want both the concrete value and a symbolic representation. Okay, so again, you don't have to do it now, but I really hope this week that some of you, as many of you as possible, will give it a try to get it installed, configured, and running. If you have problems, please ask me, because again, I've only done it for Windows. And if you have changes you'd like to make and you want to send me a pull request, I'm totally happy to take bug fixes. I'm going to be teaching this again in a summer school in Oktoberdorf in August, which is going to be much more expanded. So you can help out there, and who knows, maybe we'll even get some research out of this. Okay, so let's talk a little bit at a lower level about the requirements for doing dynamic symbolic execution. So one thing that's always sort of a first point of testing code, but not always thought about a lot, is you actually have to talk about what code are you testing. Because when you say, well, I have a program, that program might have a lot of components, and you need to talk about the code under test. That's particularly important for dynamic symbolic execution, because there will be libraries, there will be all sorts of other code that runs as part of the program, but you don't necessarily care about testing it. This is where dynamic symbolic execution is very nice. If we think of this as the code under test, oops, I'll have better luck. If we think of this as the code under test, and it has some symbolic inputs that come in, but this code under test interacts with a very large library. Okay, the nice part about dynamic symbolic execution is when you get to this interface where the code under test is calling the library, you don't want to symbolically execute the paths here. You just ask for the concrete values to call the library with. So that's very powerful, because it means you don't need to create a model of the library. You just execute it, and you don't perform symbolic execution. So when I say identify the code under test, what I mean is really you have to have some way for defining this box, which is the thing you really want to do dynamic symbolic execution on to generate inputs, and then the part of the system that it's running in that you're not concerned with testing. It's a sort of a classic code, program versus environment. So what's your program you're testing? What's your environment? The other thing for program analysis is it's very useful to normalize the code under test, and we'll see that a lot of ways. Whenever you're doing any sort of symbolic execution, if you normalize the code, put it in a normal form, the number of cases you need to deal with is much simplified. Whether that's lowering to a bytecode or doing rewriting on the AST, if you have some sort of normal form, then things that were once problematic, you can define problems away. We also need to identify the symbolic inputs. So this code under test has maybe a whole set of inputs. Some of them, I'm sorry, yeah.
What do you exactly mean with normalized?
I'll get to that. Yeah, so he asked, what do I mean by normalized? So yes, I will get to the specific. This is just sort of at the high level. So in particular, if our goal is to explore paths of control flow, I normalize in order to make those paths explicit. And I'll do some other normalization as well for other means. Often, if you want to treat loops in a uniform way, it's nice to have a normal form for loops, so you don't need to do special case on different types of loops. So we do need to identify what inputs to the cut are actually symbolic, and then we actually have to be able to trace the execution. So remember, we're going to create some inputs at random, say, or from a seed file. We're going to run the program, and we need to be able to see, we need to be able to trace the execution. Furthermore, we need to have a facility to reinterpret the instructions to compute symbolic expressions. So if I have a symbolic integer, and that's the value of some variable x, and then I say x gets x plus 1, well, there may be some concrete value for x. The new value of x is 2, but I also have a symbolic expression saying the new symbolic value of x is the previous value plus 1. So I'm actually creating a tree. Think of that as a Z3 expression or something. And then I need to also collect this path constraint. So every time the execution takes a different decision, I need to say, oh, what was the decision that was made? What was the predicate that I branched on? And I need to record that decision. Not finally, but the next in line, I need to take that path constraint and modify it somehow. Generally, I'm going to take some prefix of the constraint, keep it the same, and then take the predicate next in line and negate it. So, which is essentially asking, give me a path that's consistent with the prefix, but then goes a different direction. Then, of course, I need, if I get a new input, I need to restart the execution of the code under test. And when we say that, we mean really from the same initial state. And as you'll see in the code I'm going to show you, it's pretty suspect that you can actually do this in the way the system's architected. In this code, it uses a single process and it re-executes a function over and over again. And if there's any static state, there you can be in trouble. So most symbolic execution machines will actually fork a process or they'll restart a fresh process. So, or use a VM where you can snapshot. In this code, it's not quite robust. And then of course you have a search strategy, which is, well, you've got this path that executed, which path do you want to explore next? Okay. All right, so we're going to actually look at the code, see how it works at some level of detail, and this is pretty much it for the code. There's a loader, which you basically tell it, here's a module I want to load in and execute symbolically. It uses reflection to do that. We represent the function we're going to symbolically execute by another class. We have a set of types that represent the symbolic integer and a symbolic expression. These are both subclasses of something called symbolic type. So symbolic type is fundamentally the ability to carry a concrete value, a pair of values, a concrete value and a symbolic expression. And then there's 4 basic classes that make up the engine. We have a representation of predicates, a set of constraints, a module, a class for taking a control flow path to a constraint sequence, and then the concolic engine, which does the search procedure essentially. Okay, so the loader is pretty simple. Actually, maybe I'll just run the thing first to show you what it looks like, rather than talk more right now. Ooh, I didn't want to keep. Hold on. Yeah, so let's take a look at there. If you go into PyXZ3, you'll see this test directory, and let's take a very simple test. Okay, so the way we define a test to execute is we put it in this test directory under a name like simple.py, and the loader expects to find a function in the file of the same name, and that's the one it's going to symbolically execute. Okay, and by default, it assigns a symbolic integer to every parameter, so you can have as many parameters as you want here. And this is an open program, and essentially the engine will create a symbolic integer for each of these, and then it will do dynamic symbolic execution on this code. You can also have a function called expected result, which is essentially okay, so imagine now you explore all the paths in this code. For each one you return a value. This list here would represent that sequence of values sorted. So in general, I don't know which paths are going to be explored. I don't want to sort of code that in my test. So I essentially know that this is going to return 42 and 43. If it were the other way around, like 43 and 42, that expected result would be just as fine, right? Because I take the semantics is after I collect all the path outputs, I sort them and then just compare to this list to see if they're the same. Okay, so that's one little test. Here's another one called Diamond. So Diamond takes 3 integers. It has a concrete value for ret, and now it branches on each of those 3 and increments the return value, or increments ret by 1. So there's one case through the code which gives 0, 3 paths which give 1, 3 paths which give 2, and 1 path which gives 3 for the value. Okay, so the way we run this, pretty simple. See if I can get this a little higher on the screen. Oop. Right, so we just say Python simx.py, that's our main runner, and I'm going to run it on simple. Okay, and it basically came up with 2 values for x. One value was 0 in one path, that was the initial value. So each symbolic integer has a default value of 0. So that's one I get for free. And then the next one is from the SAT solver, which picked a value of 1. It explored 2 paths in total, big surprise, and the test passed. Here's doing that on Diamond. Okay, so you can see the values here picked again for y, x, and z here. These are 8 tuples corresponding to the 8 paths, and all the tests passed. Yay! Okay. Great. So that's the context of running. So again, the loader, you basically tell it, I've got foo.y, it loads foo.y in. The entry point, which is going to symbolically execute, is the function named foo. It's going to create a symbolic integer for each argument, and it creates this function invocation object to encapsulate this entry point and the initial symbolic values. Okay, normal form. Let's look at normal form. So in Python programs and C programs, there's lots of interesting control flow. So in a C program, you might do something like this, if A and B. Now really that control flow graph, if A and B, then go to statement S. So really that control flow graph looks like this. If A is true, then if B is true, then go to S. But if A is false or B is false, don't do S. Right? So really there's really internal control flow here, and we want to make that explicit. So fundamentally, one way to do that is you compile into the control flow graph. Well, a way to do that here would be, recompile that as if A, if B, S. Right. So now we have explicit branches, and if we wanted to really be very explicit, we would also give landing pads for each of the else branches. So fundamentally, the first two points are going to remove internal control flow from predicates to make the control flow explicit. So I want every choice on the inputs to be explicit in the code. And I also want to introduce this landing pad for each predicate evaluation. So if I have if P, but I don't have an else branch, I don't have any code to represent the false. But it's important in symbolic execution that I be able to trace each of those points. Okay, and the other aspect is to capture the predicate evaluation in a conditional into a variable. So let's just take a look at what that means for a simple program. So for our simple program here, if we go up to this SE normalized directory, we will find simple.py, and now you can see the simple program doesn't look quite as simple anymore. Forget about this SE ord thing, that's something from the code. So basically look at what happened to simple of X. So the first thing is we always eliminate the expression from the if predicate, and we capture it before the if into a special variable called symbolic evaluation SE conditional. The reason we do this will become apparent. When we're executing the if condition and we have a symbolic expression, a symbolic type, we don't want the Python interpreter to take that symbolic type and cast it to an int. We want to extract the concrete value because we're really running the program. So we have a special function that's going to be called that if second is of a symbolic type, it explicitly asks for the concrete value. Okay, but we need to also have the symbolic expression, and we want this symbolic expression in both the true and false context. So we've also introduced this which branch call, which the first parameter is just, am I the true evaluation of the predicate or the false? So I have one for the true branch and one for the false. And you see that I pass the just evaluated condition in there. So this is essentially how I'm tracing program execution for the predicates, right? I haven't shown you the overloading yet for symbolic int, but if you imagine that X is not an integer type, but is this new type that's carrying both the concrete value and the symbolic value, well, when I actually execute this condition, I really want the real value, right? So in the way I've done this instrumentation, anytime the code, the Python code really needs the real concrete value, I need to explicitly insert this cast. And so there are many other points which such a cast might be needed. So for example, we talked about before, when I'm in the code under test and I'm calling a library, where the library doesn't know anything about symbolic execution, I haven't instrumented it, I'll always want to do this get concrete at those points when I cross out from this. So this is essentially the instrumentation, the normal form that's taking place. There's a few other things going on here, but these are the basic ideas. So this rewriting is done pretty simply using, I'm not going to really go into this in detail, but the Python is very nice. It has reflection capabilities. You essentially import the abstract syntax tree module. We basically compile the code, get the abstract syntax tree, and this is the code that removes the ands and ords. So it has a visitor pattern. It's very simple to write these sort of things. So for every function that I want to symbolically analyze, symbolically execute, I need to have the source code. So so one limitation of this code is that we're not going to deal with precompiled binaries, that is PYC files. Okay, so any questions about that transformation to normal form? Yeah.
Yeah, could you also abstract from it in the sense that you said x and y, if x and y, and I just take the x and y as one thing?
Yes, oh, that's a good question. So I could have chosen, actually, the question was, did I really have to lower to remove the x and y? No, I could have kept it in the conditional. In that case, I would have had less paths to explore. So totally. So my decision here was that if I have x and y in a conditional predicate, then there are more case splits on the input. But yes, if I wanted to do abstraction and reduce the path explosion, then I could actually disable that instrumentation. Yeah, that's a very good point. Huh? I'm more thorough now, but if I wanted to be less thorough, you could actually disable that instrumentation. The important part of the instrumentation is really to capture that Boolean expression into a variable, so then I can use that variable in multiple contexts, in the concrete context or the symbolic context. Good question. Right, so that was just an optimization. Well, you could say it optimization, yeah. Okay, all right, so where's the heavy lifting done? So the heavy lifting is actually done really here. So the beautiful part of Python is it is overloading. So in order to introduce, everything in Python is an object, including integers. And so I can overload everything I like. And symbolic type, although Python doesn't have generics, you can think of symbolic type of T as sort of the base class. And it represents, it's a class that represents both a concrete value of type T and a symbolic value of type T. And when I say symbolic, there's really two types of symbolic values. One is a symbolic integer, which just represents the initial value of some integer. So it's like a Skolem constant, right? It's just a name that I give to a primary input. And that name is just a constant that doesn't change, right? And then I also have symbolic expressions. That is, if I have x gets x plus 1, well, when the Python interpreter, or when Python executes that statement and x is a symbolic type, plus will be overloaded. So if the concrete value of x is 0, the new value of x will be 1. But since this is a symbolic type, it'll also carry an actual expression tree, which will say the new value of x now is the initial value plus 1. So we're carrying two things along. And this code is not particularly interesting to look at, but we'll just take a quick look into it. The symbolic, and actually I could use help on refactoring. This class hierarchy I don't think is very nicely done. So if you'd like to help out and you have a yen for refactoring, I would love that. So, but basically you can see here the symbolic type. Here's the constructor. It has some name, so I can have a friendly name. It has a concrete value. And then the interesting part is sort of down here. So for example, Python has this lovely syntax for overloading, underscore, underscore, LT, underscore, underscore. That's the overload for the less than operator. So whenever I have x less than y, this thing will get called on symbolic types. And what this code does is it actually does two things. It has a lambda expression that says, here's the actual underlying concrete computation to do. And then it has an AST, it uses the AST to say, here's the name of the operator that this represents. And then it does this do bin op function. The do bin op function is essentially computing both the concrete and symbolic values and representing them. So it has the symbolic expression for itself and for the other parameter, so a binary. It has the concrete lambda function and the AST operation. And essentially what it does down here at the bottom is it builds a little AST tree with the left expression and the right expression. It creates a symbolic expression around that, and and that's a new symbolic type. Then it assigns the concrete value of that type to be the function evaluated on the concrete values of the left side and the right side. So fundamentally, that's all you need to do to implement the symbolic evaluator going forward. You overload the symbolic type, you overload everything that can be done, and then as Python executes the code, it's just going to be keeping this pair of the concrete value and the symbolic expression. Now, the trick is, as we said before, wherever the Python code semantics really needs the integer, the trick now is Python will just happily cast a symbolic expression to an integer, right? To whatever, however it does that, I don't know. So in those cases, I need to be explicit. I need to say, no, here, take this concrete value. So that's sort of the tricky part. The beautiful part is through the overloading, this symbolic type will propagate through the code, through the data flow. That is, if I have a variable x of symbolic type, and I do y gets x plus 1, then the dynamic type of y will be a symbolic expression. But now if y is passed to a library that doesn't know what to do with symbolic expressions, I'll need to cast it to its concrete value. Okay, so this is the beautiful part of Python. In sense, overloading is your friend for doing strongest post conditions, because you're basically creating a new value to wrap your underlying concrete value, you're adding the symbolic representation, and then the code as it executes forward is just building this expression tree for you. Actually, it's a DAG, it's an expression DAG. So any questions? Any questions about that? So in this case, we're actually not building a Z3 expression, and there's good reason for doing that. We want to keep separate our symbolic expression of Python state from the actual theorem prover we use in the end. So we're going to have another function which is going to take our symbolic expressions using the Python AST type, and we're going to write a translator to either STP or Z3. The other reason for doing that, it's also nice, there might be things we can't represent in Z3, right? So keeping it at the Python level, we then have the choice, do we substitute later some concrete value for an expression that we know we can't represent in Z3? So remember, we need the flexibility to be able to use concrete values wherever Z3 might not have a theory for us to use. Yeah?
Since you're doing that, you're keeping the whole expression. If the program is quite large, the expression may grow also.
We'll take a look at that, yes. And so it's very important that you do several things in a realistic implementation. One is you need to keep a DAG rather than an expression tree. So you want to share subterms, right? You don't want to duplicate, because you can easily get exponential explosion just through repeated sub-expressions. So let me show you an example of that. We have this little function I took from a C example. So here we have a compute function that takes x, and then we have this lovely set of assignment statements. Take x, add it to res, then take res and just accumulate it doing different operations. So now we're duplicating. Like if you used a simple strategy, each assignment statement is doubling the size, right? So you need to be smart with sharing. So you don't even need different control flow paths, right? If you just use the same name twice on the right-hand side, you're doubling. If you're naive, you're doubling the size, right? So you need to be smart about that. Okay. All right. All right. So now let's sort of see how things go together. So we need a way then. Okay. So we've got the symbolic execution going forward. You saw through the instrumentation that certain functions are going to get called. Which branch is going to get called. So let's take a look at how we get into the business of path constraints. So probably this case we'll go back and look at the code a little bit. The concolic engine itself is fairly straightforward. The loop really looks sort of like the pseudocode I showed you. So what we do is we first kick off one execution. And the first execution just uses the default values for symbolic integers, which is 0. So the first execution, every symbolic integer is 0. It does that execution and it records a path. I'll show you how it does that. Then while there are constraints left to solve, we pop the one. And in this case, it's using a generational search. So I'll show you it's a form of breadth first search. So it's got a queue, a DQ properly. It selects a constraint. It turns out the constraint could have been processed already. If so, just ignore it. It's got the new constraint. It processes it, which basically means find a new input. Then it does another execution to get the new path, and that's it. So basically, it's got a queue. It pops something off the queue. It essentially negates the last predicate, calls the sat solver, gets a new input, runs it again. Okay, so that's essentially the engine at the high level. Okay, so let's talk about how it actually gets hooked up to the constraints. Right. So path to constraint is the interesting part here. So path to constraint, this function is responsible for building up the constraint set for one execution path. Okay, so remember our nice function called which branch? So that's the one that's called in by the instrumentation. So every time you have a if that goes true or false, this is going to get called. So the very first thing we do is we look at the conditional expression that was passed into us. And if it's not a symbolic type, we don't care about it. So remember, that code that we're executing is instrumented, but that doesn't mean that every predicate is going to have a symbolic type flow into it. It may just be a concrete value. Like I could say if true, right? Or it could be a predicate that's not dependent on tainted input. So there's no symbolic type. So the first thing is I don't create predicates for things that are constant values, right? That are constant runtime value. So what I do then is I create a predicate, which is just simply a wrapper around the symbolic expression. So the symbolic expression is this cond expression. It's a symbolic type, and there's two possible predicates. One is for the branch direction that I saw, and the other is for the negation. And so there's a data structure here that we're keeping, which is essentially the tree that you saw. Let me go back to that. So essentially what happens is as I'm executing a path through the code, I go down this path, and the which branch gets called. Which branch gets called for p comma true. And I create a predicate to say, hey, I just observed p being evaluated to true. Now this is the very first branch in the procedure, so it's the top of my search tree. And so then what happens is as I go later on, I get to q, and maybe q goes false. So I'm going to create another predicate, and I need to chain that predicate to say it happened after this predicate. So I'm essentially creating a tree, a path through the tree. back here. So the predicate is just representing a branch I saw in the direction, plus the symbolic expression. Okay. That predicate then is going to be added into a constraint. So the constraint is really representing the sequence. So a predicate is just a single evaluation of an expression going some way. A constraint is a whole sequence. So here's what a constraint is. Right. So a constraint has an associated predicate. Processed means I observed it executing the way it went. So I could create constraints for predicate directions I haven't seen yet in an execution. And a constraint has a parent, which is the previous predicate. Right, so this is just a representation of a tree. It's the tree you saw with the max function, right? It's all the possible paths. Now, in general, that tree is exponential in size, but I'm only going to keep certain pointers to it for the points I haven't explored yet. Okay, so fundamentally, that's sort of it for trapping the execution. So I overload the symbolic, I use symbolic type to overload the meaning of all these operators to create these symbolic expressions. Whenever a predicate evaluates a particular way, if it's a symbolic type in the condition, then I say, ooh, that's a constraint that I want to record. And I record a sequence of those constraints, which is a path. Finally, when I process a constraint, this is where I'm going to go to Z3. So process constraint does the following. So when I execute, and this gets into the search strategy a little, but it can be factored out. So suppose I execute this path where P is true, Q is false, and R is false. So I'm going to have I really have three paths here, right? I have a path which says P true. I have another path, well, actually I have the empty path, right? Epsilon. I have a path of length 1, I have a path of length 2, and I have a path of length 3, which is at the end. So each of those is a potential to explore another path, right? So what I essentially do is I have three new constraints that I put on the queue. I have a constraint here, and a constraint here. And the first one basically says, and the processing them is as follows. When I pop a constraint from the queue, I just take the prefix before that, and then I negate the one I've currently got. So when I first explore, so after I explore this path, what will I do next? I will essentially take the first constraint, which is P true, and then I will say, is there a way to make P false? Right. After I'm done with that, there may be some new constraints that are at the end of my queue. But the next constraint I get is going to be Q false here in the context of this prefix. So now the next thing I'll do is I'll say, is there a way to keep P true and then make Q true? Right. So this is called generational search because fundamentally this is what's done in SAGE. It's neither quite breadth first or depth first. It takes you explore a path, and then you're exploring each generation off of it. Right. And you won't explore other paths until you're done exploring those generations. So there's a queue, it's a FIFO, and as you explore a path, you put constraints on. Right. And then the notion of processing a constraint is that you've seen that direction of that predicate in the context in its tree. So it's a fairly straightforward search. Okay. So let's actually go a little deeper into some of the examples so you can see this at work. Okay, so actually maybe this is a nice one. Actually, this one isn't so nice. Let's look at many branches. So this one's a very simple example. So here there's just 3 primary inputs and there's a bunch of decisions that we're making on them, and we're returning 8 different values. So expected values are 1 through 8. Let's run that one. Yeah, it passed. Let me mark this. and bring it into the editor. Okay, so the first input that it created was 0, 0, 0, right? 0 for all values. And there's the second one where it created 1, then 0, then 0, then 0, 5, 3. So it's clearly not depth first, right? Because in is branched on first, so it's this generational search. So let's take a look at the log of this and give you a little bit more idea how it's working. So it's many branches. Oh, right. I didn't. Oh, no, it should be there. There's a log file. So we have quite a bit of information that you can look at to see how it's in our debug log. So essentially, this first execution is telling us this is at the point where the which branch function is called. And so it's found a symbolic expression, and that symbolic expression is a binary operator where the left variable is this symbolic integer in 1. It's being compared to 0. And that's not a big surprise because that's the first, right, that's the first statement there. Okay, and then just to see, here it's comparing, oh, and that branch evaluated true. So was true means the branch direction. So remember, all values are initially 0, so we compare in2 to 5, that's false, in3 less than or equal to 3. So that's the first path. And what you see is that that first path yields 3 constraints, because that first path has 3 predicates, and we need to flip each one. And so the first thing we do is just flip the first one and say, oh, we want to see it not equal, variable in1 not equal to 0, and the constraint solver says, okay, assign the value 1. So that's how we get this input here. Right? In1 and in2 and in3 remain 0, and in1 gets flipped to 1. Right? Okay, so now that execution runs, and it generates some new constraints, which get pushed to the end of the log. So now we have 5 constraints left, and we've already solved 1. And now the second one we take, the second constraint we take is essentially saying, oh, don't flip the first branch. Remember, in1 is equal to 0, but we want in2 to be equal to 5. So that's why here we get 0 and 5. So these are just, these 3 inputs, if I were going to if we're going to say where did they come from, these guys were generations off that first input, right? That first input gave us 3 constraints, and these were the 3 branches we got by flipping. And you can sort of see that, right, in the values, because in these 2 inputs, in1 and in2 remain 0. They remain their default values. Okay, so that's just to give you a little idea of how the exploration is working. So any questions about that? Clear as mud?
Did you show also how libraries work, if you don't want to?
Ah, yes. So I'm going to talk about the many deficiencies of this code base in just a second. And the answer is they don't work. There's many things that don't work because this is a tiny little code base, and I am not claiming anything about robustness. So first of all, every time I restart the execution, how do I do that? Well, I just take the one file that I'm exploring and I reload the module. That guarantees that any variables in that module are reassigned, but say that module called something else that has some static state. Then your next behavior could change. And this is what I mean by divergence. If you're not careful about restart, then the next time you run the function, it may not go the path you desired it to go because you didn't clean up everything. So the first problem is it'll be very easy for people to create examples where you you diverge. The other problem is you can't explore code for which, you can only explore code for which we have source code. So if you call into a library, these libraries are essentially bytecode, generally, in the Python world. They're bytecode, and what I've shown you, that we don't instrument the bytecode. So once you're in the bytecode, you're not getting the predicate evaluations. Now it turns out the original code from the NICE project does have a bytecode parser and interpreter. For the purposes of presenting this to you, I ripped that code out and I used an instrumentation approach. The problem with the bytecode stuff is it adds a whole level of complication. So for my approach here, you can only analyze properly what you have source code for. And then anytime you go outside of the code under test, you have to call a concretization function. And I don't do that. So right now, I only call that getConcreteValue function in a predicate. So let's say you do, you have a dictionary and you say dictionary subscript X, where X is a symbolic expression. It will not work right now because I don't take that and cast that thing. So there's a project already for somebody. You know, do the rewriter that says, here's my code under test, and trap everything that goes outside for some definition of outside and insert the coercion. Or figure out a better way so you don't have to do that. But I think you have to do that. So transition from the instrumented code to the uninstrumented code is always a problem when you're doing analysis. There's the code that you've specially analyzed, and then there's the other code. Dynamic symbolic execution, as we said, is great, because whenever you go into unknown code, you can concretize, but you have to concretize. And so we need to explicitly extract the concrete value. Python will just happily execute it, no problem. It just will do very unexpected things. Right. Okay, wow, so I think I have a lot of time left.
Yeah, you have about 40 minutes, 35.
Oh, okay. So before we go deeper into some other things, my assignment to all of you students is please get the software installed and experiment with it. I anticipate it will not work the first time you try to run it because I've only done it on Windows and I haven't tested it on Mac OS or Linux, but I really do think it would be great for you to try to get it going and give me feedback. Please write and submit new test cases. It's really easy. You just drop them into that test directory. Whoa. Okay. And then I have lots of features for people to implement. So as you've seen, it's a very small code base and really easy to understand. That's the good part. The bad part is it's a really small code base and it doesn't cover all the interesting cases. Now, my goal is not to make a full symbolic execution machine for Python, but I think we can explore a lot of interesting aspects. One would be, let's make it deal with symbolic lists or symbolic arrays. So as you saw in Pex for fun, you can give an array as input to a function and it will grow the array. That might be an interesting thing to do. We might need to use Z3's theory of arrays to do that. So we're not just going to use bit vectors. There's many, I have a whole set of things from very simple to more complex. So let's see. And yes, and the other things, so there are many other things that the code is woefully ill-prepared to deal with. So one is it has one search strategy. Most of the engines like Pex and SAGE, you want different search strategies for different types of programs. So one thing might be to actually make a module that lets you select the different type of search. Okay, handling loops and procedures. The code is totally untested in the sense of what if you have a loop that depends, that says, is X less than Y, where X and Y are both symbolic inputs, or one of them is. I think right now it'll diverge in the sense of just exploring more and more paths. I have not tested it on loop programs, and we need to do something about loops. So the typical thing we do for loops is the following. You introduce a variable with some initial value, say 5, and you decrement it on each loop iteration, and when you get to 0, you say, that's the end, I'm not going to explore anymore. So this is typically, again, remember, we're about bounding the number of executions. So the typical way to do that is just define some well order, just let it execute up until some limit, and then just stop it. Okay, we could do the same thing for recursion. One interesting thing are loops that are constant but large bound. So what if I say, for I equal 1 to 1,000,000, but within the loop, I increment a symbolic variable. So that's sort of interesting, because that loop is finite, it will complete, but it could create a very large expression. We'd also want to do something for recursion. And again, with recursion, the idea is to have some sort of counter that's going to decrement and stop analyzing recursion after a while. Okay, and since I do have some more time, I know a lot of people are interested in verification, so let me spend a little bit more time then talking about some of Ken McMillan's work, which is to say, how would I actually use this sort of dynamic symbolic execution, but use it to mine proofs from the tests? So this is a very hot topic. And so unless there are other questions about the code base, I'll use the rest of the time to talk about his lazy annotation technique. Okay, so any other questions about the code?
So regarding this hands-on session, do you plan to have a session sometime later?
Oh, I didn't plan any other session, a hands-on session. I mean, I am totally available for people to work hands-on with me for the rest of the week. If we want to actually get together and discuss the fruits of our labor, maybe we could have a session later where people show off what they did, or we just discuss all the many deficiencies of this little code base. But I didn't plan on another formal session, but if there's enough interest, we can certainly organize one, right? No. Oh.
I had a question. How is it coupled to the solver?
Oh gosh, thank you so much. Wow, we completely forgot about that. Yeah, good question. Okay, so let's go back to process constraint. So this code is sort of ugly. I would write it very differently myself. But essentially what it does is it collects up the prefix. So these are the assertions that say I'm on this path. And then the expression is the thing I want to negate. So essentially the code before this, it just built up from the predicates the prefix, which is here, and then it has the last one, which is the constraint I'm going to flip, and then it has some bookkeeping stuff. Okay, so yeah. Well, you already all know how to do it. So I get it. So what does find counter example do? It pushes a Z3 context which says I'm doing some work in isolation. It asserts the prefix, then it adds the negation of the query, then it checks it. If it gets unsat, which could be, then you don't have an input. If it's unknown, we're probably in trouble. In the SAT solver case, it might be that we reached some timeout or there's some bug in the code. Otherwise, if we get down here, we've got a model. And then we take the model, as you saw before, we iterate over the variables, we cast them from Z3-ness back into Python world, and we're done. And then the rest of the code is not very interesting. It's just going from our AST representation to a Z3 expression. So if that AST expression has a bin up at the top, then translate the left and the right sides, and then we say, hey, if the root was a AST add, then take those guys and apply the Z3 add. So it's all operator overloading again. So Z3, now I have the types of Z3 expressions, and in this world I can only have these symbolic, I can only have these ints. So you see I do plus, minus, multiplication, shifting, all this good stuff. So there's a little fun part here. So it's about Z3 semantics. Oh, sorry, hang on. I just, is that pretty clear? Yeah, okay. So there's one particularly fun thing about this piece of code. So in Python, you have system integers, which are whatever the word length is, 32, and then you have big nums. And in Python, the semantics is there is no overflow. So if you have an int, a system int, and you increment it past max int, it just coerces it to a big num. But you know, you saw that hash shifting and all that stuff. Well, all those operations like multiplication, the reason I can do them is because I'm doing them on bit vectors of fixed length. So I'm actually cheating here. I'm doing a different semantics. That is, I'm treating all the integers I see as system integers, and actually when they overflow, it wraps around, it doesn't convert to big num. So Python semantics are very interesting, and in fact, there's an example there where you know, if you took the inputs I generated and gave them to a true Python program, it would behave differently. So there's a whole interesting question of, like, if you want to treat multiplication, if you're doing it for integers, for the natural numbers, then you're in big trouble. You have undecidability results for just validity, right, with nonlinear arithmetic. But with bit vectors, you have decidability. But the problem is because you're finite now. You can encode a multiplier, it's just finite, right? So yeah, so there's some interesting questions, you know, like how would you really deal with the big num issue? And the fact that you can do shift and all these other, I mean, like Python has sign extension and all sorts of interesting semantics. So yeah, I've also played a little fast and loose with semantics here. Because I'm just using bit vector decision procedures in a context where Python integers have a very interesting semantics because it changes from one type to another on an overflow. Yeah.
But this looks just like loop constraints. We can find eternal loops using some constraints on the length of the loops.
I'm sorry, say again?
I think that the problem with long arithmetic in Python and that we can test it like this, like with long arithmetic. It's like we can test eternal loops, you know.
Oh, sure. So the question is, this is just analogous to loops in programs. Absolutely right. And a multiplication operation where you have a sequence which is unbounded, multiply is just a loop, right? And so you know So anyway, there's, you know, the conversion here is very straightforward. As you see, not a lot of code. And that's the whole interface to Z3, is that one file. Okay, so I don't think there's anything really else interesting to talk about the code. I think you've seen pretty much everything. So let's pop back up. And we have about a half hour?
25 minutes.
25 minutes? Okay. Right, so let's talk a little bit about this lazy annotation. So this is very interesting work by Ken McMillan. So we have talked about DPLL. We've talked about how a SAT solver works. And Ken wants to further elaborate on this analogy between software testing and DPLL. So you saw we're searching for inputs that reach a set of given goals. In his context, he has a goal. So remember, in the case I was talking about, there was really no goal, which makes the search sort of undirected. I mean, you're exploring more and more branches, but for what purpose? So the key idea is, when you make a decision in a SAT solver and you get to a conflict, there are two things that happen. First is it does smart backtracking called non-chronological backtracking. But the really interesting part is it does what's called lemma learning. That it learns a new constraint so it doesn't make the same stupid decision again in the future, right? Because if you think of search, you know, you might have hundreds of variables and you make a decision on A, you say A is true. And then you make some stupid decisions down about X, Y, and Z. And then you make A to be false. You don't want to make the same stupid decisions about X, Y, and Z. So the idea of lemma learning is you learn from conflicts, you learn from unsatisfiable instances, and you don't make the same mistake again. Okay. So the idea is, can you apply ideas like lemma learning from SAT solvers in the case of this symbolic testing. So this is, you can see where I stole my original slides from. We have an analogy between software testing and SAT. SAT is doing Boolean variables. Software testing is making decisions on program branches. Ken says, well, in SAT solvers you do, deduction is Boolean constraint propagation, and software tests, the process of doing the symbolic execution is your implication. And then his idea is, well, in SAT solvers, you're learning clauses to prevent you from making the same mistake again. Why not do something which he calls annotations, so that when you're doing dynamic symbolic execution, you don't do that? Okay. And then he has other comments about the deduction system. So you've seen this slide already. We get some inputs X and Y. The idea of dynamic symbolic execution is we have concrete values, so we execute here, this particular branch, but we can also carry symbolic representations along the way. And then the symbolic execution gives us conditions on the inputs that produce that particular path, but then we can monkey by negating those conditions to get new constraints on the inputs to go to new paths. Okay, so as I said before, symbolic execution going forward, this is strongest post condition. So it's a form of proof that's on a program path, but we can use other proof systems. Okay, so now here's Ken's explanation of DART, or dynamic symbolic execution. So you're choosing a random input, just like a SAT solver chooses a variable. You're executing the path to get some sequence of constraints. You're finding an input satisfying some prefix and then the negation of some constraint at a point. And this drives the execution along the alternative path. Now imagine there was another path that came to that same point. Then you would just be making, you could potentially be making the same stupid decisions again, right? So just as in a SAT solver, you chose something about X, Y, and Z deep down, and then you flipped A from true to false, the same thing can happen in a program. And what I've shown you right now of dynamic symbolic execution, there's no learning. So you could be making the same mistakes again and again. Okay, so the idea is, if you want to put learning in the context of dynamic symbolic execution, you're going to make a sequence of decisions, and then at some point, you get unsat. That is, you make a decision, and it tells you you can't get to your goal this way. Okay, and so the idea is to deduce some clause that's going to force you the other way. Okay, call this. I guess, yeah. So this clause will say, this clause psi, I guess that is, will force you to say x not equal to 0, and that forces us to take the x equal 1 branch. Okay. So the idea is, like, when you reach a contradiction, there's useful information to mine from that contradiction, and if there's another context in which, well, here, I think the next slide's, okay, so here's the idea. So we've come down this path, and we're trying to get to the exit, but we were blocked. And so we got a contradiction, so we weren't able to make progress. But we want to push up in the path an annotation that prevents us from going down, making those bad decisions again. So we have this blocking condition psi, and what are its properties? So when psi is true at this point you can't get through to the exit, okay? You can't reach the goal via this edge. And so if psi is true in this state, maybe even via a different path, we're forced to take the other branch. So psi is something we learned from sort of going down this edge, that if it's ever true in some other context, we don't need to go that way again. Okay. So the idea is we want to avoid sort of the exhaustive backtracking by learning. Okay, and this annotation psi is going to help us. So this is essentially the context, which is very similar to what we saw in our code base. So one thing that's a little bit more advanced feature that we might do is we might take the Python interpreter and we might actually try to get it to learn annotations. And so here's the idea. We have a couple of rules. So we're going to compute a path constraint. And along that path constraint, we now have reached a symbolic state S. So that symbolic state S is an assignment of symbolic expressions to variables. And then we have an edge E, a control flow edge E that we want to take. Think of that as a branch in the program. And we are going to annotate somehow, using some technique, this blocking annotation, psi. And what does that mean? It basically means that if psi is, if for some other state S prime not equal to S, if S prime implies psi, we don't need to go to further. We can just explore somewhere else. Okay. Now the other thing is we need to push these learned annotations up the control flow graph. So suppose I've learned, oh my gosh, is that phi and psi? So if I've learned on all the outgoing branches of a predicate different blocking conditions, then I want to derive a blocking condition at S, and I do that by conjoining them, right? So basically, if I've blocked an edge, and I've blocked all the outgoing edges, then I can block the statement, and I can push that back up, right? So what I'm doing is I'm using contradictions, but from exploration to learn these blocking clauses, and as I get more and more of them, I can push these blocking clauses further up the control flow graph, and that gives me more and more pruning at higher levels. Okay, so let's take an example. So this might be a nice example to put into our Python symbolic executor. So in general, diamonds give us exponential paths, and here, so what do we have here? We have a condition here, which is a branch, one side in which x is equal to 0, and the other is x not equal to 0. And our goal state is to say, so our question is there an execution path that gets us to the goal state here, which requires that x is not equal to 0, right? So initially x is not equal to 1. So really, if we had foresight, premonition, we would just always go the right side, and then we'd be happy. But we don't know yet, so we might make bad choices, right? So we might make a bad choice here, a bad choice here, a bad choice here. And we might explore, say, 7 paths before we find the one path out of 8 that takes us to the goal state, right? And remember, we're not doing backward execution here, we're doing forward. So you might say, well, why not start with the goal and push back? But that has other problems, like weakest preconditions, your expressions blow up. So we're doing it in a forward context. So we choose so imagine, these predicates depend on other inputs other than x. And so what happens is, we choose some path, and maybe that's a really bad path that goes down the left side. And because of that, we don't get to the goal. Okay, so now we're at the end of this path, and we need a blocking condition. And the blocking condition is essentially going to be, the blocking condition is essentially going to be x equals 0, I guess, right? We don't want to see x equals 0. And actually, I'm not going to go into all the details, but on the left-hand side, the blocking condition is true. On the right-hand side, it's x equal to 0. And the conjunction of that is x equals 0 at this point, right? And so now we've learned an uninteresting fact, right? If x is equal to 0 at this point, we definitely won't get to the goal, right? And now that condition can be pushed backwards, essentially, through a local form of weakest precondition. And so in Ken's work, he shows how you can essentially push x equals 0. Once you've learned on that one path, you can push it back up. You can push it back up. Oh, wow. Okay. let me get there. So you can push it back up to this point, okay? And then when you explore the other branch and come down here, okay, you're always going to pick the right-hand branch, because you've essentially annotated things to guide the search in the right way. Okay, so fundamentally, he can reach the goal in a linear number of backtracks, right? Rather than having to relearn, oh, I shouldn't have selected the branch that caused me to assign 0 to x. So there might be exponentially many ways to assign the wrong value to x. But here he can learn an annotation that he pushes up the control flow graph that says, don't choose the direction where you're going to pick x equal to 0. Okay, so that's essentially the idea there. And he also generalizes it to procedures. So the idea is a very powerful one, and it's really taking this idea from SAT solvers and bringing it back into programs. So you can, just as you learn lemmas and SAT solvers to print the search space, you can do this annotation business in programs. And you can potentially get exponential reductions. It doesn't say that you aren't left with an exponential in the end. So we can go into more details about that as needed. Let me just say a little bit about loops. So again, this is essentially what I explained before. If we have loops or procedures with recursion, we're going to use an artificial ranking to force termination. Okay, and so this is this is sort of the bounded model checking way, and along with that, then what Ken has been exploring is ways to guess inductive invariance. So what you would like to do is come up with some summary of the loop that allows you to prove that it has no unsafe executions. But that's way beyond what I want to talk about here. Right. So Ken has explored this idea of lazy annotation and compared it to Dart, essentially the procedure that we talked about in the first lecture. And so the idea is, how long does it take you to generate tests with 100% statement coverage? And so they compared this on, Ken compared this on a number of examples. And the learning algorithm here is essentially reaching high coverage in much less time than Dart, which is been shown here. So the Dart-like procedures, which I've been showing you about, or dynamic symbolic execution, really do have a problem with exponential blowup, and there are many techniques to deal with that. Okay. And yeah, he has a bunch of, yeah. So let me just finish with his conclusions here. I think it is, this idea of dynamic symbolic execution, as you've seen, is really another form of search, which is very much like model checking or SAT solving. And a really key idea in the SAT solver is to learn from conflicts, to learn these lemmas. So the idea that Ken has been exploring, and I think is interesting, there's still research left in that area, is to learn these annotations during dynamic symbolic execution, and then use those with some form of generalization to try to actually find a program proof. And that's been the goal of a lot of the work that Shyam and I did originally on the SLAM model checker and other examples. Many of the automated proof techniques are really looking at a finite set of counterexamples and trying to generalize from them and learn enough predicates to form a proof. This lazy annotation is unique in that it gives you a way to think about leveraging dynamic symbolic execution to do this form of proof. Okay, so I think with that, we'll finish up.
Thank you very much. Thank you, speaker first. So we still have about 5 minutes.
Great.
Any questions?
This lazy annotation stuff seems very much like the work done in the dash algorithm in the Yogi tool for Microsoft.
I'm probably not the best person to talk about that. He does have, his paper has a more specific, so Dash is splitting, as I recall, is splitting on frontiers, right? Using the weakest precondition. But I don't think it's doing the learning propagating back up. So when you have this conjunction, these conjunctional blocking clauses, I think Ken has examples where the Dash Yogi stuff has, and it's not hard in this case, it does exponential splits, and Ken reduces that. So, his form of blocking plus the conjoining, I think somehow is superior for certain examples. There may be other examples. I don't know that that's a theorem. It just may be cases. But there's definitely, state partitioning is part of these approaches, right? You're learning new predicates and you're partitioning the state. And I think my basic understanding is that he somehow gets by with less partitioning for certain types of examples.
Okay, yeah, I did see the exponential blow up in the backwards direction, so that makes sense.
Right.
Are there any other questions?
I've got the lazy annotation paper, so it has more details on that. We could go through that. Yeah. No, it's fine.
Okay. I was just wondering, now you apply it to white box testing. What if you want to apply it to black box testing, where you get a model? So in a sense, you have your formal model. I think there's also work by Microsoft done on that. But would that make it actually easier because you have your explicit model,
right.
So you don't have to...
Right. So the question was, well, what if you don't do white box, but you do black box, and you have a model that talks about the expected behavior? Well, then you can do your exploration at the model level. So you can do, essentially what Spec Explorer does is it does dynamic symbolic execution, if you will, at the model level, and then has a conformance test against the implementation. Yeah, that's absolutely a good, a fine thing to do. This is the case where we don't necessarily have the model, or the model is maybe very simple, like preconditions, postconditions.
But could you also then use what you get back from the implementation under test in order to guide your, for example, you know that you want to end up here, but you don't know, normally you cannot compute everything to force a certain path through the system under test. So if you get back the concrete values from the system under test, that sounds a bit like then you can apply the algorithm that you discussed by basically
I think I understand. So,
the symbolic values in your model.
Right. So I think the question is, if you get these values back from the implementation, then you might be able to say, okay, so these output values that I saw given this input, I don't want to see that again. I don't want to see, you can negate, you can sort of,
For example,
right, you could say that behavior has been covered, I don't want to see it again, which basically means don't show me that particular input again. But why would you use okay, so you might have some assertion about the input with respect to the output that at the model level that might help you prune the search potentially.
Yeah, well, I'm actually interested in that direction because for the test generation part, you of course also have this blow up.
Yeah, sure.
Which you might. Well, I was triggered by your slides, but maybe we can cut down on the number of paths that we have to generate and explore by using this.
Yeah, okay, I'm happy to talk about that more. Yeah.
Okay, if there are no more questions, we will go to lunch now. There is a kind of a main aisle where you can pick up